Problem 3 on the Kinematics Example worksheet. A new driver is traveling 30 meters per second on Cartwright Road when suddenly another car pulls out in front of him. He knows that his car is capable of slowing down with an acceleration of -3 meters per second squared. How far will the car travel before it comes to a complete stop, and how long does it take for the car to stop? Once I read the problem, I'm going to go ahead and write down G for given, and then write down all my variables that are possible. Then I'm going to reread the problem. A new driver is traveling 30 meters per second. That's the initial velocity on Cartwright Road when suddenly another car pulls out in front of him. He knows the car is capable of slowing down with an acceleration of -3 meters per second squared. That's our acceleration. How far will the car travel before it comes to a complete stop? That's 0 meters per second. And how long does it take for the car to stop? Okay, they do not give us the initial position. Like I've talked about previously, if they don't give you the initial position, most of the time it's a benefit to you to set that at 0. So we're going to set that at 0. You could picture on a displacement versus time graph, you start at on the y-axis at 0. Okay, our unknown. We're looking for how far will the car travel, which is delta D, the displacement, the change in position. But since we set the initial position to 0, the change in the position is equal to D1. Also, it asks how long does it take for the car to stop, and that is time. Our equation for part A, we're going to take our 4 equations and we're going to go through and try to find one that will find D1. The first one finds D1, but as you notice, we don't know time, so we can't use this one. The second one does not find D1. The third one does find D1. We need to know D0, which we have. We need to know V1, which we have. We need to know V0, which we have, but we don't know the time, so we can't use that one. And then the last one does not require time. Let me see if we have all of the variables. We need D1 in the equation, which we've got. We know V1, we know V0, we know A, and we know D0. So we can use this fourth equation. I'm going to substitute, and I have 0 meters per second squared equals 30 meters per second squared plus 2 times -3 meters per second squared times D1 minus 0 meters. Okay, and then we're going to solve. So I've got 0 times 0 is 0 meters squared per second squared equals 30 times 30 is 900 meters squared per second squared plus 2 times -3 is -6 meters per second squared times D1. I'm going to subtract 900 from both sides and then divide both sides by -6, just using Algebra 1. And I end up with 150. So D1 is equal to 150 meters. Okay, do the units work out? Let's see. If you divide meters per second squared by meters squared per second squared by meters per second squared, everything cancels but meters in the numerator. And so we do have correct units. That's one way to check your work, is to do the math on the units. If you end up with the right units, more than likely you've got the right answer. So part B, we are looking for the time. So we'll go back through our equations and try to pick one that's fairly easy. We know everything in this equation now. but except for time, so we could use this one to solve for time, but it's a parabola, so it's quadratic. Maybe we don't want to use that one. This one's linear, so linear equations are good. We know V1, we know V0, we know A, so we could solve for t using this one. So let's do that. And I've got V1 equals V0 plus A times t. I'm going to substitute, and I have 0 meters per second equals 30 meters per second plus minus 3 meters per second squared times t, and subtract 30 meters per second from both sides, and divide both sides by minus 3, and we end up with 10 seconds equals t. Okay. Let's see, let's draw our graphs. This time we have a little bit different scenario. We have an object that is moving in the positive direction, but it's slowing down instead of speeding up. And so one way to think about this is to draw lines representing average velocities. So we start out with a displacement versus time graph where we start from 0. The object's moving in the positive direction, so it has a positive sloped trend, and we could draw it maybe like that. It's positive slope, but that slope decreases because the object's slowing down. So we would draw another one that has less slope, and then less slope, and then less slope. Looks like a curve to me. A concave down parabola. So that would be our displacement versus time graph. Our velocity versus time graph is going to look a little different too. We've got to put 0 here just to show that I'm going to start with a positive velocity. I'm at 30, but I'm going to go to 0 over the 10 seconds, and it changes at a constant rate. And this slope is the acceleration. The slope of the the slope of the velocity versus time graph is acceleration. And so then our acceleration versus time graph, we've got 0 up here, and the acceleration versus time graph is constant and it's negative.